Hi folks, Dr. K here with today's Science Untangled topic on real and ideal gases. So what actually is an ideal gas and why does it matter? Now, just to take a step back, when we're looking at gases, we can start off by considering some history. Boyle looked at the relationship between pressure and volume and found that the product was a constant. Charles, in turn, looked at volume over temperature, which also turned out to be a constant. As you can see, the graphs look something like this. And finally, Gay-Lussac also looked at two of the possible variables. In his case, he looked at pressure over temperature, and that also turned out to be a constant, resulting in this kind of graph. All of these assume, of course, that all the other variables stay the same, okay, stay constant. Now, those things together were then turned into what has become known as the ideal gas law. And in the ideal gas law, of course, we have pressure times volume being equal to the number of moles times the gas constant times the temperature, okay? A few things to notice there. First of all, the gas constant can be expressed in a range of ways. So if you need to look it up, make sure you've got the right one, okay? The top one tends to be the norm, but you will run into others. Second point is that pressure and volume can also be expressed in different ways. So you need to be careful with the units there. You need to be careful with how you are given the information before you simply plug it in, okay? So be careful with the units, okay? Temperature, of course, needs to be in Kelvin for this to work properly, but examiners have a tendency to give it in Celsius just to make sure you're paying attention. Now, an ideal gas, just to get back to the title here, what is an ideal gas? What makes an ideal gas? For an ideal gas, the first assumption is that the particles themselves have no volume. They're treated as points in space, okay? The second one, there are no forces between the particles, neither repulsive nor attractive, okay? Now, clearly we can't have a perfect situation where that's the case because there just wouldn't be anything there. But if we have relatively low pressure, okay, so the distances are pretty big, and we have high temperatures so that the kinetic energy factor outweighs any other forces between the particles, then we can approximate it, okay? Now, how then is a real gas different? Well, because of those particular issues, right? And before I get into that, if you like what I'm doing here, please like and subscribe and leave a comment with feedback to help me keep the channel going. So, differences. Pressure. Pressure, as I already said, it is influenced by forces between particles. Pressure is particles bouncing off a surface. So, if you have particles that are more attracted to each other, they'll bounce off the surface less often. If you've got particles that are more repelled from each other, then they'll bounce more often. So it has an effect. Okay, we don't need to worry about the exact effect, luckily, but there's an effect. Second, particles have a volume. They're atoms at a minimum, right? So the available volume in your container is less than the total volume of the container, right? All of that leads to the van der Waals equation here, where the pressure has a correcting factor and the volume has a correcting factor. Okay, now you will normally not have to worry about this equation. Okay, I wanted to make sure that I showed you the equation so that you have an idea of where it's all coming from, because that's the general idea here. What you may very well be asked about is those factors. What influences things? What decides whether something is an ideal gas? How is a real gas different? So qualitatively, you may be asked to comment about it, okay? And to go back to that comparison then for a second, with my final question here, if we assume values for the constants A and B in the van der Waals equation for oxygen, what would the volume be of 1 mole of O2 at RTP using both of the equations, so both the van der Waals equation and the ideal gas equation, the ideal gas law? How much difference is there actually when you look at it under sort of comparable circumstances? Okay, so here are your values for A and B. Have a go. Convert as needed, of course. Have a go. What's your answer for that volume using either of those equations, and how do they actually compare? Okay. Well, that's it again for today on this one. I am looking forward to seeing what you come up with, and like, subscribe, and leave a comment, please. Thank you.